Hi there. Today we're working on piecewise functions. You guys just took a test over graphing different parent functions with their transformations. So this is a little bit of the same work, but now we're actually taking a piece of that graph because there's a restriction on the domain. So when this says y equals the square root of x plus 1, we know that that graph is the square root graph that moves left 1, and it usually looks something like that. But we're only going to show the part where x is greater than or equal to 3. So the first thing I want you to do is take that restriction on the domain, whatever that value is, and plug that into the original function. And when I plug that in, I get 3, 2. And that's going to be a key point. So that's going to be like a starting point for you. So I can graph 3, 2. There's the coordinates. It touches 3 right there because we're going to show the part that is greater than or equal to 3. So that's to the right this way. And we can label that key point. Okay, so here's another one. Y equals negative x cubed. It's the cubic that's been reflected. So the graph usually looks something like this. Plug in a 0, we get 0, 0 right there. We're going to show the part that is less than 0. So it's to the left like this, and really that should be a hole right there at 0, 0. And you can erase the rest of this graph because we don't need that. That's not part of the answer. Okay. Let's look at number 4 there. You've got the cubed root of negative x. So a cubic that's been reflected over the y-axis, and it moves up 2. So the graph looks something like that. And if I plug in a 1, I get the cubed root of negative 1, which is negative 1, plus 2. So I get a positive 1. So the point 1, 1 is our starting point. And we're going to show the part that is greater than 1. So something like that. We can erase the rest of this. Also, if at any point, if you want to find an intercept, we could always just plug a 0 in for y there. We get the cubed root of negative x plus 2. Subtract the 2 equals cubed root of negative x. We could cube both sides. So a positive x would equal a positive 8. So that point was 1, 1. This point is 8, 0. So sometimes that'll help you get an accurate graph. So when you're graphing these, you can make your graphs look really nice. Here's one with multiple functions, and you can have as many functions as the problem asks for. This one, you've got your absolute value, that's your V graph. When I plug in a negative 2, I get a positive 2. Down here, when I plug in a 0, I get negative 2. So the first one, we're going to go to negative 2, 2. It touches that point. It's inclusive right there. And we're going to show the part that is less than negative 2. So that is this graph right there. And then this one, we're going to start at 0, negative 2. It doesn't touch 0, so I'm going to put a hole there. My slope is 3, so up 3 and over 1. And there's your graph. Make sure when you're graphing multiple functions, make sure you check to make sure that your end result, your final piecewise function, is a function. Make sure that it passes the vertical line test. If not, then you messed up somewhere and you need to go back and figure out where you messed up. On this bottom part, this is very simple. if you're asked to find f of 3, you look over here and you ask yourself where does 3 lie on this graph? Does it fall into this quadratic here, or does it fall on this linear right here? Well, the quadratic goes all the way to 3, but it doesn't touch 3. So since it doesn't touch 3, then we can't find f of 3 of the quadratic. This one does touch 3, so we'll ask ourselves the first question, where is 3 on the graph? And once you figure out which function to plug it into, then you just make sure that you plug it into the correct function. So here I'll plug 3 into the second function because it falls on that domain, and I get a -1. F of -2 is less than 3, so that one I use this function and I get a +4. Okay, let's skip down to the bottom one here. K of 16. This is less than -2. This is between -2 and 1. This one goes all the way to 16, but it doesn't touch 16. And this one's greater than 16, and it does not include 16 either, so that would just be undefined. On number 13 there, the 0 falls between -2 and 1, so I'm going to use this function. So when I plug a 0 in, I get 3. Okay, a couple more problems that you're going to see would be something like this. Here's a graph for you. Now, as you're looking at this graph, I'll just go and leave that. As you're looking at this graph, hopefully you can notice that there's 3 different graphs here. Okay, 3 different functions. You've got a reflected parabola here. You've got a cubic right here in the middle, and you've got a linear. So this is practicing what we did this past week. This parabola right here, like I said, it's reflected. If that's your vertex, it went left 1 and down 1, so we would write the function with all the transformations. And then you state the domain. So it's been restricted. We're only showing the part that is less than -1, so you'd write it like that. There's no stretch or shrink, because if this is your vertex, it went left 1 and down 1 as your next point. So there's no stretch or shrink there. Now in the cubic, same thing. From the 0, it went left 1, down 1. It went right 1, up 1, so there's no stretch or shrink on this cubic. There's no horizontal or vertical movement, so there's your function, x cubed. It's just the parent. And we're only seeing the part from -1 to +1. Then the last one is this linear. Going from this point to this point, we would see that the slope is 2 over 1. And then from there you could go down 2 and over 1 and see that your y-intercept is -1. So there's your mx plus b. And the domain for that graph is from 1 to 2. Okay. Notice if I include the 1 here, then there's no need to include the 1 here. If this one goes all the way to 1, then don't include it right here. Okay, now the last problem that I want to show you is right here. We're going to find t so that h of x is continuous, and then you're given h of x right here. So they're telling you that it's continuous, so that just means that it shares a common point. These two functions share a common point. We're trying to find what this stretch is for this quadratic. So this is the best way to set it up right here. Your 2 will help you. That's your domain there. Your 2 will help you find your key points. So I plug 2 into x cubed and I get 2/8. When I plug 2 into tx squared, I get 2/4t. Since it's continuous, they have to share this common y value. They have to share a common point there. So we'll just take 4t and set it equal to 8 and solve. And we get t equals 2. So we just found the stretch for that quadratic. So hopefully this will help you when you're working with piecewise functions.